Thank you for joining our presentation about an innovative spring capture technology we call the CODEINSE method. I am Julie Wildschut, Professor of Civil and Environmental Engineering at Calvin University. I'm also a licensed professional engineer with a research focus on green stormwater infrastructure and improving access to clean water.
And I am Derek Tempass. I'm a recent civil environmental engineering graduate from Calvin University. And starting in January, I will be a master's student attending Iowa State University. The Clean Water Institute of Calvin University is a research institute in Grand Rapids, Michigan, founded in 2014. With the goal of advancing sustainable water treatment solutions across the globe, the Clean Water Institute partners with existing agencies to tackle problems with an interdisciplinary approach. Faculty and students from engineering, chemistry, political science, public health, and more are actively engaged and design projects to create lasting solutions in attaining clean water while providing life-changing experiences for students. Last summer, our research team worked on a project based in Ecuador. What does access to drinking water look like in Ecuador? Well, in Ecuador, only a little more than half of rural Ecuadorians have access to safely managed drinking water services. And this impacts a good portion of the Ecuadorian population, with a little more than 1 in 3 rural Ecuadorians being served by rural community water systems. Many of these rural water systems rely on freshwater springs as their main water source. Typically, these springs have been protected using traditional spring capture technologies, such as spring boxes and subterranean spring captures. CODEINSE, our research partner, has worked to develop a new method of spring capture. CODEINSE is an engineering firm founded by indigenous Ecuadorian engineers who build relationships with communities and empower them through helping them build and maintain clean water systems. CODEINSE reached out to the Institute for research assistance in collecting data to determine whether their new spring capture design was an improvement on traditional methods.
Derek and I did not do this work alone. Our research team was comprised of engineers and chemists from both CODEINSE and Calvin University.
Here's a roadmap of our presentation going forward. We will first discuss what our team did in Ecuador when visiting rural communities. Then we'll have a few slides on the analysis we conducted on data from said communities. And finally, we'll spend the majority of our time discussing the key design elements of the CODEINSE spring capture.
In Ecuador, our community visits focused on 3 main things: bacterial testing, chemical testing, and site analysis. We conducted a simple coliform test quantifying the amount of fecal and non-fecal coliform bacteria present in the captured water and on nearby surface water. We measured physiochemical parameters of the water, such as pH, turbidity, and electric conductivity. We also tested for elements such as iron, sulfate, nitrite, and nitrate to begin to create a chemical profile of our water source. Our team also visually inspected the spring capture site, taking pictures of water system fixtures and noting possible contamination risks, as well as recording answers to interviews with the water managers. All of this data was collected in multiple surveys using an Esri app called Survey 123. This allowed us to georeference our data, as well as created a space to go back and input the coliform numbers when the colonies were fully grown. We gathered data from 41 different drinking water sources, most of which were engineered spring captures employing one of these 3 methods. The spring box was the most common method surveyed in the rural communities that we visited. This method uses a poured-in-place concrete box that surrounds the spring eye. It aims to protect the spring eye from water surface with its impervious cover, but it can be subject to damage from erosion and is sensitive to poor construction methods. The subterranean spring capture was another traditional method of spring capture we observed. This method uses a slotted PVC pipe with a gravel pack backfilled with soil on top. While this method can collect vast amounts of water from less defined water sources, it is susceptible to surface water contamination through inadequate filtering through the ground cover above the collection pipe. The CODEINSE method draws inspiration from these 2 traditional methods using a combination of a slotted piping, gravel filtering, and also concrete protection.
We performed a comparative analysis for our bacterial water samples by classifying each site according to spring capture method and WHO risk levels. The WHO standard for high-quality water is defined as the absence of coliform-forming units. However, the presence of microorganisms in water is not a uniform level of risk. The assessment of microbial risk to a water system is quantified according to the displayed classification from the WHO, where an increasing level of microbial contamination is associated with an increasing risk assessment level. We then used these risk levels and our geospatial data to create a map to use as a helpful tool for initial analysis. As you can see on the map, most CODEINSE spring captures were in the none to low risk categories, while only one spring box and one subterranean system were in the none category. A map is nice for visual aid, but we had not yet answered whether the CODEINSE method was an improvement on traditional spring captures. To determine whether CODEINSE spring captures were different than traditional methods, we used a chi-squared analysis, bidding counts of low microbial risk and high microbial risk water into CODEINSE captures and traditional method categories. Our chi-squared analysis determined that the CODEINSE method was statistically significantly different at a 99% confidence interval compared to traditional methods. We then turned to our coliform counts to see if this significant difference was an improvement. In this figure, you can see 4 different lines representing the 4 different water sources surveyed. On the y-axis is the WHO risk levels, and on the x-axis is the percentile of spring capture. Your best quality scenarios for each type of capture lie on the left side of the graph, starting at the top 25 percentile. As we move to the right, we eventually land on the worst case scenario for each water source. As you can see, for every water source that isn't CODEINSE, the worst case scenario sources are providing very high risk water. Meanwhile, CODEINSE spring captures provided no risk water for 50% of samples taken.
So what made the difference? What is it about the CODEINSE method that resulted in cleaner water? We identified 4 key design elements that, when combined, sets CODEINSE's system apart from traditional methods, and when employed, should result in safer drinking water. During the site evaluation, designers should gain an understanding of the natural flow of groundwater in the area. Water is naturally filtered, and bacteria can die as it flows through the soil, so the length of time water flows through the soil impacts the distance you need to evaluate and protect. These images here are portions of the survey tool that we used to evaluate the site. Using this tool, we identified contamination threats from animal scat, latrines, and ponded surface water, as well as the protection quality from fences, tanks, and covers. After locating a safe site to source drinking water, it's time to implement a CODEINSE spring capture. Implementation involves the remaining design elements of clean water collection, surface water elimination, and limiting system exposure. Groundwater is generally considered to be microbially pure, so the idea behind this method is to capture the water, keep it clean, and make sure the easiest flow path is into the pipe for distribution. This starts with excavating the site all the way to the spring eye or the seeps and stabilizing the surrounding soil. Laying a gravel pack with a slotted pipe provides a path of least resistance for the water to flow into the distribution system. Finally, a cutoff wall located at the downstream side of the gravel pack creates head and encourages the water into the pipe instead of seeping into other places.
Once clean water is in the system, it is imperative to protect it from contamination in the distribution system. All capture sites displayed a range of surface bacteria present. However, there was no statistically significant difference between protection types. As a result, the contamination of water systems seems to arise from the intrusion of surface water. The CODEINSE capture seeks to eliminate surface water exposure at the capture site through plastic and concrete covers. In addition to limiting exposure at the capture site, it is vital to eliminate opportunities for recontamination throughout the distribution system. The use of overlay tank covers for collection tanks, as well as taking care to eliminate pipe gaps surrounding inlet and outlet pipes, is key to protecting the clean drinking water.
Another aspect of the CODEINSE method that cannot be overlooked is the social aspect. These springs are initiated, constructed, and owned and maintained by the community, households. Households that want to connect to the system provide sweat equity for construction and pay for the water that they use. These fees pay for the aguatera or water manager who maintains the system. CODEINSE is in continual relationship with the communities, is available for consultation, and hosts hygiene classes. In at least one community, the system was so well taken care of that the community has saved over $40,000 to reinvest in community development. In another community, households were able to sell their cow milk at a higher price because of the improved quality milk after switching to the new system. And in all cases, the overall health of the residents has been improved. In conclusion, after collecting and analyzing water from 41 different sites, we determined that the CODEINSE method does provide cleaner water than other methods, and we identified 4 key design elements: site evaluation, clean water collection, surface water elimination, and limiting surface exposure through the system that seem to contribute to this improvement. Currently, we are working on a detailed report that includes the technical design elements and will serve as a manual for other communities. Our future work will consider chlorination in gravity systems. Thank you for listening to our presentation, and I believe we have time for questions.